welcome to Lecture 33, 9.1, Estimating Population Proportion. Okay, so first off, we're going to look at obtaining a point estimate for the population proportion. So if we wanted to find out how many adults in Hawaii had traveled to Las Vegas, it would be unreasonable to survey the entire population. Instead, we would use a sample. Let me go ahead and write that down. So a sample of the adults in Hawaii to create an estimate of the proportion. This is called a point estimate. Alright, so by definition, a point estimate is the value of a statistic that estimates the value of a parameter. So example 1, obtaining a point estimate of a population. Suppose that Jessica surveyed or conducted a survey of students that were in the Windward Community College library to see how many students had been to Las Vegas, and found that of the 524 students she surveyed, 325 of them said that they had been to Las Vegas. Obtain a point estimate for the proportion of Windward Community College students that have been to Las Vegas. So, if we're going to do a point estimate for the population proportion, we would do p hat is x divided by n. And in this case, our x value is going to be the number of students, the number of students that said they had been to Las Vegas, and n was the total sample. So the number that had been would be 325, and n is going to be 524. So if you plug that into our calculator, what answer will we come out with? So let's see, 325 divided by 524. We get p hat is about equal to 0.62. So what does this mean? Well, this means we estimate. Oops, spelled that wrong. Go ahead and erase that. So we estimate that about 62% of WCC students have been to Las Vegas. Period. Okay, so now let's take a look at Objective 2, constructing and interpreting a confidence interval for the population proportion. Okay, so one of the problems with this is, recall that in statistics, the samples we find would vary from sample to sample. So what if the survey had been done at the student bookstore instead of at the library? We would get a different random sample, right? Which would result in different point estimates. Because there is a possibility of different proportions, we need to report a range or interval of values, including the likelihood that the interval included the unknown population proportion. So in statistics, we're going to construct an interval for a population based on a guess, okay, along with a level of confidence for our guess. For example, you might say, I'm 50% confident that my mom is at home, right? Or maybe if you're more certain your mother would be at home, you'd say, I'm 90% confident that my mom is at home. Okay? You would have a guess, and maybe your confidence is higher or lower. All right? That's just an example of guess with a confidence level. Now, the guess is the point estimate of the population parameter. And the level of confidence plays a role in the width of the interval. That's talking about how big our confidence interval would be. Is it large number, like 95% confident, or is it small, like maybe 50% confident? So I'm going to go ahead and just take a moment to draw a figure. So if we have, let's say, this interval, and this is our guess. Maybe we're talking about the mean, right? We say our mean guess is, I'm going to go ahead and write an example. So let's say we said our mean was 45. That's our guess based on our point estimate. Remember, which is from a sample. So it's not actually the mean of the population, it's the mean of the sample. And after that, we could have a small level of confidence. Let's say, well, it should be, some certain numbers. So this would be a lower level of confidence. And then we might have a slightly higher level of confidence, which is wider with our guess still inside of it. Alright, so let's take a look at the definition. By definition, a confidence interval for an unknown parameter of an interval of numbers is based on a point estimate. Now, the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as 1 minus alpha times 100%. Good one to remember. Real quick, let's do a review on the sampling distribution p hat for the sample proportion. So, if we're looking at the shape of the distribution of all possible proportions, it's going to be approximately normal, provided that, remember, our sample times the probability of 1 minus the probability should be greater than or equal to 10, and the sample size is no more than 5% of the population size. What else? Well, the mean of the distribution of the sample proportion equals the population proportion. That is, mu of p hat is going to be equal to p. And lastly, the standard deviation of the distribution of the sample proportion, or the standard error, is what? Well, sigma p hat equals square root of p times 1 minus p divided by n. So just a reminder on p hat. Now note, whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. Any sample statistic, that's a hard word, it kills me. Any sample statistic, I got it. Alright, that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. And now note, real quick, so we have the value z sub alpha divided by 2 is going to be called the critical value of the distribution. Real quick to note, if you wanted to take a look at some of the technology and just sort of a visual on level of confidence, go ahead and read example 2 in your book. Now, so for a small chart on level of confidence, here's the main level of confidence we tend to look at, 90%, 95%, and 99%. Now, when we work with those, if we're talking about the area in each tail, so what I mean, let me go ahead and just draw a quick image of what we're talking about here. If you have your curve and you have, let's say, the areas here on each side of the tail, so the total area would be alpha, but the area of each tail would be alpha divided by 2, right? Alpha divided by 2 for each area, but the total area is alpha. Now, if we have a 90% confidence interval, the area in each tail would be 0.05. And the critical value for that, we're just going to go ahead and give that since it is used often, 1.645. Then for 95%, the area would be 0.025. And the critical value is 1.96. Then for a 99% confidence interval, area in each tail is 0.005, and critical value is 2.575. So notice, if our value started to get a lot closer to 100, the area is going to be almost basically 0. Won't be equal to 0, but it's getting closer and closer to actually being equal to 0 as our confidence gets bigger. Now let's take a look at interpretation of a confidence interval. 1 minus alpha 100% confidence interval indicates that a 1 minus alpha 100% confidence of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. Alright, so let's take a look at an example. In a poll conducted by the Gallup organization, 54.9% of those that were surveyed considered the amounts of federal income tax they had to pay as fair. Gallup reported its survey methodology as follows. Results are based on telephone interviews with a random sample of 1,016 national adults, aged 18 and older. For results based on the total sample of national adults, one can say with 95% confidence, so they're pretty confident, right? 95% confident that the maximum margin of sampling error is 4 percentage points. Determine and interpret the confidence interval for the proportion of Americans aged 18 and older who believe the amount of federal income tax they have to pay is fair. Alright, so what are we going to want to do here? So basically, remember the confidence interval is basically equal to the point estimate plus or minus, so the upper and the lower bound, of the margin of error. So if we want to find the confidence interval, which I'll go ahead and abbreviate as CI, and you're allowed to do that, so the confidence interval is going to be equal to, well, we need our point estimate. And what is our point estimate? Oh, that was the value we had right over here, the 54.9%. And then what is the margin of error? Well, it tells us the margin of sampling error is 4 percentage points. Okay, so we're going to go ahead and turn these values into the decimals. So 54.9%, what is that as a decimal? That's going to be 0.549. Now plus or minus, and the margin of error. Well, the margin of error as a decimal is going to end up looking like, well, we're talking about 4 percentage points, so that's 4%, right? Which is equal to 0.04. Go ahead and plug that into our equation. And now we have our confidence interval is equal to these two following amounts. So I'm going to go ahead and split them. 0.549 plus the 0.04, and CI equals 0.549 minus the 0.04. Alright. Calculating this out, we'll end up with 0.589. And lastly, confidence interval is 0.509. Okay. So what does this mean? Well, remember, we're talking about with 95% confidence. So we have that we are 95% confident of what? Well, that the proportion of Americans aged 18 and older who believe that what? Well, that the amount of federal income tax is fair is between, we have found our upper and lower bounds. So it's going to be between this value and this value. And actually, what I should do to label these correctly, this should be the upper bound and the lower bound. A better way of labeling this, or a more correct way to label it. So this would be upper bound. Let me go actually change the color on this. So the upper bound for the confidence interval, and this would be the lower bound for the confidence interval. Alright, so the upper bound and lower bound, well, it's going to be between 0.589 and 0.509. So we're 95% that confident that our proportion of people who agree would be between about 50% and 58%, or you could say about 51% and 59%. Somewhere in between there. We're 95% confident that our proportion falls in there. So let's go ahead and draw an interval on the side here. So we went with 54.9, but our interval of confidence we had was 50.9. I went ahead and changed it back to percentages here, and 58.9. And we are 95% confident that the proportion falls in between these two endpoints. Alright, so constructing a 1 minus alpha times 100% confidence interval for a population proportion. So suppose that a simple random sample size of n is taken from a population, or the data are a result of a randomized experiment, and our 1 minus alpha times 100% confidence interval for p is given by the following quantities. So our lower bound is going to be p hat minus z alpha divided by 2 times the square root of p hat 1 minus p hat divided by n. Kind of looks like what we've been working with before. And then p hat plus z alpha divided by 2 times the square root of p hat 1 minus p hat divided by n. So once again, the main difference between these two, or the only real difference, are the minus and plus signs. As usual, lower bound always has the minus, upper bound's always got the plus. Now note, it must be the case that we have n times p hat of 1 minus p hat is greater than or equal to 10. And that's something we've been working with a lot before. And also, as usual, what we've been working with is our sample size needs to be less than 5% of the population, where the lowercase n is our sample size and the capital N is the population size. So we need these two requirements in order to construct the interval. Now let's take a look at a definition. So, by definition, the margin of error capital E is what we give it. Once again, note, if we're given E is capital, the margin of error is capital E, make sure to use a capital E. Don't use a lowercase e. That would be marked wrong. So, in a 1 minus alpha 100% confidence interval for a population, proportion is given by the following equation. So, our margin of error is going to equal to z alpha divided by 2 times square root of p hat times 1 minus p hat over n. A lot of these equations are pretty similar. So example 4. In the Parent Teen Cell Phone Survey conducted by the Princeton Survey Research Associates International, that's a mouthful, 800 randomly sampled 16 to 17-year-olds living in the U.S. were asked whether they have ever used their cell phone while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. Obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who text while driving. So what's the first thing we should do? First, we're going to go ahead and compute p hat. So first, p hat. And p hat is going to equal, remember, our x divided by n, where n is our sample size, which was 800, and x is the ones that fit our criteria. So that'll be 272 divided by the 800, and that'll come out to about 0.34. Actually, that comes out to exactly 0.34. Let me go ahead and fix that. Alright, so once we have found p hat, what should we do? We're going to first have to make sure to verify the two requirements that we had, which were n times p hat needs to be, or n times p hat times 1 minus p hat needs to be greater than or equal to 10. And we also have to satisfy the n should be less than or equal to 0.05 times the capital N, so our population size. Okay, so let's go ahead and check this one out here first. So our n size is 800 times p hat, which was 0.34. 1 minus 0.34, is that greater than or equal to 10? Well, when we calculate it out, we get 179.52, which is indeed greater than or equal to 10. So check, that's good. And now, for this one here, basically the population of the U.S. is going to be way larger than 800. So it's safe to say that 800 is less than 5% of the U.S. population of teenagers. All right. So we've got those two criteria down. What is the next thing that we should do? And one thing to note, it is important to make sure to show me that you are checking the criteria for different items. So always make sure to check them. Basically, the main criteria you're looking at is the sample size working. So the first one, n times p hat, or in some problems it's just n times p. And then also that your sample size is maybe less than the 5%. So the next thing, what should we do? Well, we want a 95% confidence interval, right? That's what we're looking for. So we want 95% confidence interval. So what does that mean? So we have, and for a confidence interval, remember we're using 1 minus alpha times 100%. That should equal our confidence interval. And then we're looking at 95. So we'll end up with, this should equal 95%. So solving for alpha, we'll get 1 minus alpha equals 0.95. And then 1 minus 0.95 equals alpha. And we end up with 0.05 is equal to alpha. Now remember, for our formula, we need z of alpha divided by 2. So let's go ahead and find that. Then z of alpha divided by 2 is going to equal z of 0.05 divided by 2, which is z of 0.0, and what is that? 25. And we had that given in the table above, so we're looking for 0.025. And what value was that? Right here, critical value, 1.96. So I'll go ahead, write that down, 1.96. And let's go ahead and substitute these into the formula. So the lower bound is going to equal p hat minus, what was our formula? Right here, upper and lower bounds for our formulas. And we're looking for p hat minus z, let me rewrite that, z alpha over 2 times the square root of p hat times 1 minus p hat over n. And the upper bound is going to be the exact same, except we have a plus sign instead of that minus. Just rewriting the formulas so you guys can see where they are. I'm going to go ahead and color code this so we know where everything is going. Well, p hat, we have that we're plugging in these places. And then z alpha divided by 2 is going to go there. And lastly, or not lastly, we have n, which is going to be our 800. And that is it. Okay, let me go ahead and write those values in. Alright, so I went ahead and filled in the formulas. So let's go ahead and calculate that out with our calculators. So if we plug that in the calculator, we'll get 0.307 and 0.373. So what does this mean? Well, actually, first off, we do want the margin of error. And the margin of error, if you recall, or if you notice in the formula, the margin of error is actually just this portion. So the margin of error, E, when you actually calculate that out, so let me go ahead and write this on the side. E is going to equal the 1.96 times the 0.34 times the 1 minus 0.34 divided by 800, which comes out to, let's see, plug in calculator, 0.033. Okay, so that is my margin of error, capital E. We have my lower bound, upper bound, all of those values. So what does this mean? Well, remember, we're looking for a 95% confidence interval. And we start it with, we are 95% confident of what? Well, that the proportion of 16 to 17-year-olds who do what? Well, who text while driving, is between 0.307 and 0.373. So once again, let me just go ahead and draw a small image. I'll go ahead and box it off here. So basically, we're saying we had about, our p hat was about 0.34. Remember, it's a point estimate. This is not actually the mean of our population, because we're just looking at a sample, but it's the mean of our sample. But since it's not the actual mean, we have to create the confidence interval. So with our confidence interval, we said, well, we can safely say, with about 95% confidence, that our mean is in between 0.307 and 0.373. Okay. So example 5. Using the same data from example 4, determine the effect on the margin of error by increasing the level of confidence from 95% to 99%. So remember, in this example right above here, we were using a 95% confidence interval. So now we're going to take a look at what it would be if it was a 99% confidence interval. Well, first off, for 99% confidence interval, we're going to look at the alpha times 100 equal to, and this time we're using 99%. Solving for alpha, 1 minus alpha is equal to 0.99, and then 1 minus 0.99 is equal to alpha, so we have 0.01 is alpha. Okay. Next, we need to find z of alpha divided by 2, which is going to equal z of 0.01 divided by 2. That simplifies out to z of 0.005. Once again, let's go ahead and look at our table to figure out what that is. We're looking for a confidence interval of 99%. Area in the tail, yep, and 2.575. So let's write that down, 2.575. And let me just go ahead and move this over just a little bit. Alright, so there we go with our confidence interval. Oh, no, sorry, not a confidence interval. Our z, alpha divided by 2. Now, let's go ahead and use the formula. And remember, our p-hat value from previously is 0.34. And our n value from previous was 800. That was our sample size. So, we're looking for the margin of error, recall? And for the margin of error, we're going to use the formula. Z alpha divided by 2 times the square root of p-hat 1 minus p-hat divided by n. Let's go ahead and color code these values so we see where they're going. So that's that. Here's our z value. Then we have, oh no, that's not something, and then our p-hat. So it's just going to change by a little bit. Let's see, so 2.575 square root of 0.34 times 1 minus 0.34 divided by the 800. And what do we get E equals? E is going to be about 0.043. So that would be our margin of error. So our margin of error is 0.043, period. Not too bad, that one. Alright, so one thing to note. The bigger the sample size, or the larger the sample size, the more precise of an estimate we are going to end up getting. And this is just by the law of large numbers. Now let's take a look at 3. So determine the sample size necessary for estimating a population proportion within a specified margin of error. So this time we're sort of looking at, we want a certain amount of error. Okay, we don't want too much maybe. Right, you don't want that much error when you're working with things in real life. So let's say you have a certain amount of error and you're asking, what size population do I need to get so that my error is on the smaller size? So suppose that you want to estimate your proportion with a specified margin of error and a certain percent confidence. How many individuals should be in your sample? So first let's take a look at the actual formula for error, right? This is the formula for margin of error. We were just introduced that. Now what we're going to do is solve for n to create a formula for sample size. So let's go ahead and solve for n. If you want to pause the video and try to solve for n by yourself, go ahead. Might be kind of fun. First things first, I'm going to go ahead by multiplying both sides by the z value. Or actually, We're going to be dividing both sides by the z value. I'll just times it by the reciprocal. Okay, that cancels that out. Then we're left with e divided by z alpha over 2. It's going to equal the square root of p hat 1 minus p hat divided by n. Now, to get rid of that square root, we'll go ahead and square both sides. That'll cancel that square root. And we have e z divided by alpha 2 squared is p hat times 1 minus p hat divided by n. We are slowly freeing the n. How will we get n by itself? Well, let's go ahead and cross multiply. This is technically over 1, so cross multiplying. We'll end up with n times the e divided by z, z alpha over 2 squared is going to equal p hat times 1 minus p hat. Well, we still haven't successfully solved for n. To do that, we're going to need to divide both sides by the e over z alpha over 2, or we could multiply by the reciprocal. But let's just go ahead and, I'm going to go ahead and multiply by the reciprocal. There are a few ways to do this. This is just one of the ways that I just sort of came to my mind first. So let's go ahead and divide by the, or multiply by the reciprocal to get rid of, wait. Let's rewrite that. A lot of little symbols going on here. Alpha 2e squared z alpha 2e squared. Okay, these guys cancel each other out. And we're just left with n on one side, huzzah, p hat 1 minus p hat times z alpha over 2 divided by e squared. And there we go. We have the formula for finding the sample size. That would be good for a specified margin of error. So if you're given a margin of error, we can find our sample size. As long as we have p hat, our margin of error, and our z, so our confidence interval. If we have those three items, then we can find our sample size that we would need. So let's take a look at the sample size needed for estimating population proportion p. So the sample size required for a 1 minus alpha 100% confidence interval for p with the margin of error e is given by the following formula. Well, this was the formula that we just found. I'm going to go ahead and write it down. Okay, and remember, this is going to be rounded up to the next integer, where p hat is a prior estimate of p. So if a prior estimate of p is unavailable, then the sample size required is just going to be n equals 0.25 and then times z alpha with our margin of error squared, which is going to be rounded up to the next integer. Now, so note, the margin of error should always be expressed as a decimal when using the above two formulas, okay? So don't use a fraction, keep with a decimal. Example 6, determining the sample size. So, an economist wants to know if the proportion of U.S. population who commutes to work via carpooling is on the rise. What size sample should be obtained? So we want to know n. If the economist wants an estimate within 2 percentage points of the true population of 90% confidence interval, with 90% confidence if. So you have two options. The economist uses the 2009 estimate of 10% obtained from the American Community Survey. Alright, so note, this is giving us an old estimate. So this would be p hat, which is a prior estimate. Then we're given our confidence of 90%. We'll use that to find the z. And we have our estimate point within 2 percentage points. So that is going to be our e value. So, well, we have, what do we have? We have E is going to equal 0.02, because that's 2 percentage points. Then we have that P hat is 10%, which is 0.1. And what else do we have? Well, we know that Z of alpha divided by 2 is going to end up equaling Z of, and we're given a 90% confidence interval, which, remember, it correlates with, let's go ahead and take a look at our chart up here. 90% correlates with, ooh, so far ahead. Here we go. 90% correlates with 1.645. So let's go ahead and write that down. Whew, here we go, back to the problem. Scroll, scroll, scroll. All right. So that equals, what did I say? 1.645. Ooh, let me change my pen. Aye. 1.645. So we have all of those pieces of information. Let's go ahead and use those and substitute that into our formula. So notice we had a prior estimate, which is why we're using this formula, not the one with the 25%. That would be if we didn't have a prior estimate. But we do. So we're going to go ahead and use this formula. And that'll be the Z alpha divided by 2 over E squared. So let me go ahead and once again color code this so we know where everything's going. And let's write this down. 0.1, 0.1, 1.645 divided by 0.02. So you might say, how much of this work do I need to show on the exam? Well, if you wrote this in, so if you wrote down your formula, you wrote your filled in values, and you went ahead and just showed me the calculated value, that would be good. Alright, so just as long as you show me that you've plugged in the information correctly, you knew what the formula was, and you got the answer. That is awesome. So we'll go ahead and round this. Remember, we have to round it to the next highest number. So that'll be 609. So the economist must survey 609 random selected people. Now, the next problem, it says the economist does not use any prior estimates. So when we're not using any prior estimates, we're going to use this formula right here. So we'll use n equals 0.25 times Z alpha divided by 2 divided by E squared. What do we need to fill this in? All we need is our Z alpha divided by 2, which we know is 1.645, and E, which we know is 0.02, the margin of error. So let's go ahead and plug these in. Once again, we're using this formula because we're not using any prior estimates. And then, so just show that you know to plug these values in, you had the correct formula, and then you can show the calculation, which will come out to 1691.3. And remember, we need to round up, so we'll round it to 1692. So what is this saying? So, the economist must survey 1692 people. Randomly selected. Wow, these are two very different values. If we used a prior estimate, we would only need to survey about, let me change that. We only need to survey about 609 people. But if we don't use a prior estimate, we need to survey a lot more people than that. 1,692. So if we don't have a prior estimate, the sample size needs to be way bigger. That's kind of interesting. Alright, that is it for 9.1. Please email me any questions.